All right, what's up, Jits? We are back at it again. This video is to cover the first chapter of the A-level content. We have Lattice Energy, chapter 19. Make sure, I guess just kind of like as a little background check for this chapter, maybe refresh yourselves on the enthalpy chapter from the AS content, because that is essentially, chapter 19 is essentially a step beyond the enthalpy that we learned from the AS level content. So make sure you kind of got an idea of that in your mind as you're going through this. But other than that, let's get right into it. So, Lattice Energy. As the title of the chapter says, we are learning right off the bat two new types of enthalpy. We have delta H lat, which is lattice energy. This is defined as the energy released when 1 mole of an ionic solid is formed from its gaseous ions. So lattice energy, I'm just going to put those standard conditions there. Lattice energy is very similar to delta H formation, except lattice energy is specific to when we have atoms in their gaseous state. So here's a good example. So right here, the gaseous ion of sodium plus the gaseous ion of chlorine can combine to form sodium chloride, right? This is an example of lattice energy because the reactants are gaseous ions. Delta HF would be if these were in standard states. So this is delta HF, and that's delta H lat. So just kind of building a foundation understanding of the difference between these types of enthalpies. So let's dive a little deeper into the science behind this stuff. It's good to know delta H lat is always exothermic because think about this, right? Delta H, the lattice energy value, has to do with we're going from gaseous ions that combine to form a solid. And if you remember from chapter 6, enthalpy chapter from AS level, making bonds is exothermic. And since delta H lattice is literally only making bonds, it's going to be exothermic. So that's going to be always negative, always a negative value. So now let's understand what affects delta H lattice energy. So we have to first understand that I'm kind of going in order that the textbook presents it, but I'm also kind of jumping around. So if you're trying to follow me, just understand that I'm all over the place at some moments. So, 1 second. Okay. What affects lattice energy? Before we get into that, I guess I could. Sorry, I do not structure these videos at all. I'll go over it briefly. I'll come back to it later. So basically, we have to understand that lattice energy is when these gaseous ions combine, right? And we also have to understand that the more negative the enthalpy change of a reaction is, that means obviously the more exothermic, but also the more feasible it is because that means it's more spontaneous. So let's compare something. Let's look at the delta H lat of magnesium chloride, right? MgCl2. And let's look at the same thing for NaCl. Now, is this the example the book gives? Oh, it is. Cool. Okay, so the delta H lat of magnesium chloride is negative 2526 kilojoules per mole, right? Oh, don't mind that. The delta H lat for sodium chloride is negative 787 kilojoules per mole, right? Oh, that was embarrassing. I forgot to turn on Do Not Disturb. So as we can see, we have a much more exothermic reaction with magnesium chloride than we do with sodium chloride, right? And the reason for this has to do essentially with electronegativity. But in a sense that we don't really know yet. It's kind of the idea that the stronger the attraction between your two ions, the more negative, the more exothermic your reaction is going to be. So what I mean by that is magnesium, right, has a 2+ charge. Sodium has a +1 charge, right? So this magnesium is more electron deficient than this sodium is. So what does that mean? Essentially, when this is trying to bond to the Cl- atoms, right, this bigger deficiency creates a bigger difference in charge between the ions. And as we know in nature, the bigger the difference between two things, the harder they come together. Think of differences, like think of, on a space station, we have airlocks so we can stabilize differences in pressure. It's essentially the same thing here. So the bigger that difference in charge, the stronger they're attracted to each other, and thus the more exothermic the reaction is. What's also important to understand is that being more exothermic not only means the reaction is more feasible, what it also means is that the ionic compound formed is also stronger, which makes sense because they're coming together with a bigger attraction, with that bigger difference in charge. All right, so that was kind of a little tangent. I'll touch back on that later to fully understand or to fully explain the trends of delta H lattice. But now we're going to talk about another enthalpy that we learned. We're looking at delta H atomization. So what atomization essentially means is it's the enthalpy that defines essentially it's like sublimation, going from a solid to a gas, or I don't know if I got that the right way around. I don't know. Yeah, sublimation is solid to gas, deposition is gas to solid, whatever. But delta H atomization defines the change of energy going from a solid. So the example they gave in the book is lithium as a solid going to lithium as a gas, right? Now, obviously, this is always going to be endothermic, right? Because we're going from something that's solid and we're turning it into a gas. We are breaking bonds, right? And breaking bonds, as we know, is endothermic. So this has a positive 161 kilojoules per mole delta H of atomization. So the actual definition for this, let me see if I can get it in the book so I don't lie to you guys. Where is it? Sorry, I'm pirating this book from the internet, and I don't think it has the definitions. Oh well. Okay, so I'll do this from memory. Actually, I have my notes on me. Let me just get that like an idiot. All right. Sorry, guys. Quick little break. Okay, so delta H atomization is when 1 mole, so the energy change when 1 mole of gaseous atoms is formed from its corresponding element. So that's the ACE definition of it. But in short terms, we can understand it to be the energy change. We're going from solid to gaseous. Now, this type of reaction is very useful to this chapter because we're going to learn how to utilize this enthalpy change as well as some other ones to use a Born-Haber cycle, which is essentially an upgraded version of Hess's law to find lattice energy values. So branching off that idea, another enthalpy or another energy change that we're going to be looking at is electron affinity. So you may have heard of this from last year. But basically, electron affinity is the opposite of ionization energy. So if you remember from last year, ionization energy was the amount of energy required to remove 1 mole of electrons from 1 mole of a gaseous atom to form 1 mole of gaseous ions, right? Electron affinity is the opposite. So electron affinity is the energy change when we add an electron, right? So plus E. So for instance, the example they give, here's one with chlorine. Chlorine is a gas currently with a charge of 0, right? This undergoes its first electron affinity to make chlorine minus, which has a enthalpy change of negative 348 kilojoules per mole, right? So now, excuse me, keep in mind, this is first electron affinity because it was the first, EA1, it was the first electron that this chlorine atom gained. If it were to gain a second electron, so going from chlorine minus, keep in mind this is while it's still gaseous, gaining a second electron to Cl2 minus, that would be second electron affinity, right? And the interesting thing about electron affinity, this isn't like a crucial thing to know, but there's a possibility they could throw out this on the question on a test. Second and third electron affinities, they most likely won't ask you for an electron affinity beyond the third, but second and third electron affinities are always not exothermic, endothermic. So your first electron affinity for most atoms is going to be is going to be exothermic, like we saw with this chlorine, which makes sense because ionization energy is endothermic because we're removing an electron. That takes energy. It's like, trying to pull a magnet away from another magnet. That takes energy. But, excuse me. But with second electron affinity, it's always endothermic because of this, right? Let's say I'm going to draw the valence shell for chlorine, right? So this is the valence shell for chlorine, right? It's got 7 valence electrons, right? Once we add an electron, or actually let me do oxygen and chlorine so I can show both affinities. Whoops. Once we add our first electron, right? Our oxygen now looks like this. 1 second. And then let me get this guy, right? So now that we've added an electron, we have increased the charge density of this atom, right? So it is now more negative. And that means that when we try to add another electron, so this is our second electron, well, now we're trying to cram a negatively charged thing into a more negative space. And as we know, like charges will repel each other. So this greater negative charge means that this oxygen will actually repel this electron more than it attracts it, which means our reaction now requires outside energy to take place, meaning it is now endothermic. So that's the reasoning behind that. Trends in electron affinities. Your trends for electron affinity follow very similar to ionization energy, and for the same reasons too. So essentially, you probably remember how ionization energy got greater the more electronegative you were, essentially the closer to fluorine. Electron affinity is essentially the same thing, because think about this, right? The more electronegative you are, the more you're going to attract electrons, right? And the more you attract electrons, well, the easier it is for you to gain that electron. So, therefore, the more exothermic your, I don't know, I'm drawing a delta H, the more exothermic your electron affinity. So it follows trends similar to ionization energy. It's just more electronegativity, greater attraction of the electron, more exothermic. All right, here's the what I mentioned earlier. We're getting into good old Born-Haber cycles. So let me draw this out. Whoops, that says Bond. All right, Born-Haber cycles. Second time around, here we go. Basically, this is the more complicated version of the Hess's law cycles from the AS content. The first Born-Haber cycle we're going to look at is the one that relates delta H lat with delta H formation and another delta H, kind of it's a mix of things, you'll see. But on the top of our triangle, we're going to have delta H lat, which starts with our gaseous ions, as we saw from earlier, and that forms an ionic compound. Then the other parts of our triangle come down to form our, sorry, this should not go this way. I drew the arrows the wrong way, whoopsies. This is our elements and standard states. So I'm just going to draw elements not, right? So as we know, going from elements and standard states to an ionic compound is really, that's just delta H formation. We all know that, right? And going from elements to gaseous ions is a collection of steps that we simply group as delta H1, right? So let's understand first how these things relate to each other. As we know, if we're trying to find the value of delta H lat, right? Well, look at our indirect route. It follows like this. So delta H lat, would simply be, we're going against delta H1, so negative delta H1, and we're going with formation, so plus delta H formation. So, as you can tell, delta H formation is equal to delta H lat plus this collection of steps from delta H1, right? Let me see what example we got here. Okay. So that's how these three things relate. But now what we're going to do, we're going to expand on what delta H1 really means, and we're going to construct this as what's known as an energy level diagram. So pay attention, right? Let me find the example they give. We have the formation of lithium fluoride. So, okay, here's our energy diagram. To first understand this, we have to get our principal, or our kind of two main forms of compounds. So the first one on top is going to be our lithium and fluorine ions, right? These are as gases, keep in mind. And at the bottom, we're going to have LiF, lithium fluoride, as a solid, right? So as we know, look at this, right? From our triangle, going from gaseous ions to our ionic compound, aka going from this platform down here, let me extend this, but going from this platform up here to this platform down here, that is our sacred delta H lat, right? And keep in mind, the direction of your arrow, so how this blue arrow is pointing down, that means that the reaction is negative, as in it's exothermic. So keep in mind when you're constructing these energy diagrams, what the direction of these arrows actually mean. Because the idea behind energy level diagrams is that we can kind of think of this as being like on a graph where the y-axis is energy, right? So literally, the fact that this bar up here is above this one below means it has more energy, which makes sense because these gaseous ions have more energy than a solid compound, right? And the downward arrow means there is a loss of energy, which is what an exothermic reaction is, right? So now we have to now understand where on this delta H formation would lie, right? So we know delta H formation is going from, is going from standard states, elements and standard states to our compound. So what that would look like would be this. Or actually, a platform here, right? That's going to be solid lithium plus 1/2 of fluorine gas, right? And now, here's the thing. Does this arrow go up or down? Well, if you know that the formation of lithium fluoride is exothermic, you would know the arrow goes down. But also, we have to, there's another way to recognize is that delta H formation, because like the place where your arrow starts, like notice how this arrow starts up here? That signifies that these are my reactants. Had I drawn the arrow this way, not only would that signify that the reaction is actually endothermic, it would also signify that my reactants are this. So make sure that when you're drawing these arrows, not only are they pointing the right direction, but they're starting in the right place. So I know that for formation, our reactants need to be our base elements. So the arrow is going to go like that, right? So now, this is delta H formation. So we're almost there. Now, this is what, going from here to here is what delta H1 is. It's a collection of steps. So what are those steps? We have to let's look at the elements individually, right? Let's look at lithium first. We went from solid lithium down here to a +1 gaseous ion of lithium at the top. So how do we go from solid to gas to a gaseous ion? Here's how we do it. First step is delta H atomization. If you remember from earlier, atomization was the process of going from a solid to a gas, right? So that delta H lat gets us to gaseous lithium. Perfect. Now, how do we get it to +1? It needs to lose an electron, right? Well, what is the process of losing an electron called? Ionization energy. So that's how you would get to that +1 lithium, right? I don't have a lot of room, but I'll try my best to keep doing this. You're supposed to make it so that each platform shows one step. I am kind of out of room, so what I'm going to do is raise up this upper platform. Right? +1/2 F. Oh, that should have been F2, my bad. Whoopsies. So that gets us Li plus as a gas, +1/2 to F2 as a gas. So, lithium, because remember, the whole part, this collection of steps on the left side is going to be our delta H1. So let me get back to this. So our lithium, sorry, that does not look like a G at all. Our lithium is now complete. That matches what that top bar shows. But now we need to get our fluorine to do the same, right? So what do? You might be thinking, well, we don't need to do atomization because fluorine is already a gas. And that's a decent idea, but it's incorrect. The reason for that is because we have to recognize this is a single atom, a single ion of fluorine, right? In this part of the equation, that is F2. That is a diatomic bond. Just because we have this 1/2 doesn't mean it's a single atom. It's still F2. So, to get it in the form of a single fluorine atom, we still apply delta H atomization. And in doing so, that would get us Li plus as a gas plus F as a gas, right? So now, our last step, how do we get fluorine to go from no charge to a -1? It needs to gain an electron, right? Well, what do we call that? Electron affinity. Am I right? So, I messed up. So, okay, so here's a common error that you might see. Here's the thing, right? I drew my platform for this step. I drew it below this step right here, right? And that might not seem like an issue at first, but look at this. If I were to draw the arrow for the electron affinity of fluorine, well, I know that first electron affinities are negative, right? So, but look at this. If I were to draw this arrow, that arrow has to go up to get to that platform. So I know that means this. I know that means this platform actually needs to be above this top step. So keep in mind, the first steps that you write out don't need to be your highest or lowest step. You can extend beyond them. So what I'm going to do, I'm going to rewrite this. So what that means is that my previous step needs to actually extend beyond the top. So I'm going to draw it like this. So this was delta H atomization. And then here's our next platform. We have Li plus, I'm not going to write the state symbols, and F, right? So now that I'm above, now I can draw an arrow that points in the right direction. That's going to be EA1. And boom, we have gotten our fluorine to match what we need, right? So here's what we do from here. Let's say from this, it wanted me to calculate, it's like, okay, based off the diagram, find delta H lat, right? Find delta H lat. So, as we know, it's also, I'll explain it in the form of the diagram. So basically, we can understand, because like as I said earlier, the height at which the platform exists represents its energy, right? So we can think of this diagram as essentially a different way of representing our Hess's law triangle. So what we can do, let me explain that. Basically, I know that going from this platform to this platform, right, that has some change in energy, right? Which in this case happens to be delta H lat. But I also know that I can go from this platform down to this platform. Instead of taking this path on the right side, I can instead take this path on the left side that goes all wonky like this, right? So what does that look like mathematically? The path on the right side is equal to the path on the left. So the right side path was delta H lat, right? And the left side path was a combination of steps. It was first electron affinity. It was delta H atomization. It was ionization energy. It was another delta H atomization. And then enthalpy of formation. So what you do is we're going to follow this very similar to our Hess's law of triangles, right? So we're going to literally trace our steps back across this diagram. So I'm going to start at this platform because this is the platform I started from when defining the right side path. So I'm starting from this platform still, right? My first step is to follow this arrow to get up here, right? Well, in doing so, my path goes in the opposite direction of the arrow that's been defined, right? So just like Hess's law, when you go in the opposite direction of an arrow, you make a negative. So this is going to be not just electron affinity 1, it's going to be negative electron affinity 1, all right? So next step, now, I'm here on the platform, right? Because I've made this first step. I now, to continue my journey, need to go down, right? And guess what? Once again, my path conflicts with the defined arrow. So this becomes a negative value. So negative delta H, that was the atomization of fluorine. Plus, same thing. Need to get down to this platform. That goes against this arrow. So the negative of the ionization energy, right? Same thing. Go down here. I'm against this arrow. So that's going to be plus the negative of the atomization that was of lithium. And then for this final step, I'm going with the arrow on this final step, so that stays normal. So plus delta HF. So from here, they'll give you values for some of these, all these but one, and then you solve for the one that you need to solve for. It's that simple. So from here, it's simple algebra. But that's the concept behind a Born-Haber cycle diagram. It's just a more spread out, more intricate Hess's law. But just keep in mind, the big concept behind this is that the height of the platform represents its energy. So, be familiar with how to manipulate that concept to set up equations like this. All right. A little side note, let's say we had a Born-Haber cycle thing, right? Let's say we had magnesium chloride. Let's say we had to, I'm just going to do like a shorthand example, right? Because the tricky part of this is setting up, because all of these sub-steps of what we thought of as delta H1, that's the tricky part of this. So I'm going to do like another little practice delta H1, right? So let's say we have magnesium chloride. This is a very good example as a solid, right? And let's say we want to get this to its ions, which is Mg2 plus 2 moles of Cl minus as a gas, right? Because we have to understand that to achieve lattice energy, we need to get our elements in their gaseous ion states, right? So finding delta H, finding the other path of that reaction is essentially how do we get from standard to these gaseous ions, right? So first step, I know I need to separate this magnesium and chloride. How can I do that? By using the inverse of enthalpy of formation, right? So that's going to look like this. So that's going to give me Mg as a solid plus Cl2 as a gas, right? And now what I need to do is get things, let's look at magnesium first. I need to get this to a gas. How do I do that? Enthalpy of atomization, right? So that gets us to Mg as a gas. This needs, now, I'll write out the chlorines, Cl2 as a gas. Now, this magnesium needs to get to a +2 charge. So I have to make it lose 2 electrons. Keep in mind, losing 2 electrons is not the same thing as 2 times the value of first ionization energy. Ionization energies vary throughout which electron they are losing. So I have to do 2 separate steps. One is IE1 for magnesium, and the second step is IE2 for magnesium. So I'm like out of room, but this would get you Mg plus and then Mg2 plus, right? So once again, I've ran out of space, but I'm just gonna work with it from here. So now chlorine, right? Kind of like looking this as like a separate chart. Unlike an actual question, you would want to keep everything in one diagram. I'm just doing this because I ran out of space, but like keep everything in one diagram like we did up here with this previous question. So how do we deal with the chlorine problem? Well, as you might have guessed, we need to atomize chlorine because it's like, oh, well, it's currently a gas. Yes, but we have to isolate these atoms. Currently, these atoms exist as a diatomic molecule. We need to isolate them. So to do that, keep in mind, we have 2 chlorines in this case, right? So we need to do 2 delta H atomizations of chlorine. So that would be our next step, right? Then, once we get there, that would get us 2 moles of Cl as a gas. Then from here, we would do this again, not the same thing. From here, we would do 2 electron affinities of chlorine. So you're probably wondering, well, hold up. For magnesium, we did 2 separate ionization energies. So why aren't we doing 2 separate electron affinities? Well, pay attention, right? It's not because we're adding 2 electrons to the same atom. We are simply adding 1 electron to one atom and then adding 1 electron to another atom. So that's what we're doing. We have 2 atoms of chlorine, 2 moles of it, right? So we need to do 2 electron affinities because it's 2 separate atoms. So then that would get us to the 2Cl minus, right? So that's what I meant to accomplish by this separate example was pay attention to when you have ions that have different charges like this 2 plus and when you have different moles of certain ions. So that, knowing the difference between multiple ionization energies or multiple electron affinities and knowing when to just multiply it. All right, so the next thing this book covers, factors affecting lattice energy. So here's where this is what I was touching base on from earlier. All right. So I need a cough drop. Okay, whatever. We're gonna power through this, all right? So the next part, what is it? Factors affecting delta H. So, as from earlier, you probably remember that I mentioned the idea of electronegativity. It's essentially kind of the same concept. We have to pay attention to ionic radius, so the size of our ion, and the charge of the ion. So here's how this works, right? From the one mentioned earlier, there was the lattice energy of magnesium chloride, I should say. And then there was the lattice energy of sodium chloride. So what I mentioned earlier was that the lattice energy for magnesium chloride was much more exothermic, and that had to deal with this 2+ charge. And that was because that 2+ charge meant a greater electron deficiency, which meant essentially a more dense positive charge within that ion, right? So if here's your like Mg ion, then here's your Na ion, right? This 2+ charge means it has that bigger deficiency than just a plus charge, right? So the other thing we want to look at, do I have a periodic table on me? I should probably get a periodic table on me. I do have a periodic table. So get out your handy-dandy periodic table. The other thing to note is look at this, right? On the periodic table, magnesium sits to the right of sodium. And what does that mean? Well, we know that as you go across a period, you have smaller atomic radius, right? Because you have greater nucleic charge, which decreases the distance of that valence shell from the nucleus, right? So, what does that mean? Not only does this magnesium have less electrons, but that positive charge is confined within a smaller space than sodium. So you can think about it like this. We can understand, we all know density, or I guess rho is the symbol for density. Density is mass per unit volume, right? So we can kind of think of charge density as charge per unit volume, right? So for magnesium, our charge value is higher because it's 2+, and our volume is smaller because it has a smaller radius, right? So we can say that's V1. For sodium, that's only 1+ over its volume. We know that V1 is smaller than V2. So therefore, 2+ over V1 is going to be much greater, I wouldn't say much, than that, meaning it has a greater charge density. That's kind of like a somewhat computational way to think of it. But that also leads us into another topic of kind of like the reasoning behind this trend. It's called ion polarization. So here's the thing, right? You remember how I said that magnesium has that greater positive charge, has that greater charge density? Here's the thing. When this interacts with the anion, so in this case, that anion is going to be chlorine. So I'm just going to draw it as, I'll draw it as two separate ions, right? So here's our chlorine ions, right? Cl minus, Cl minus. What happens is this positive charge actually distorts our ions. So instead of being perfect spheres, we're going to look a little oblong like this, right? Because it's literally pulling those ions toward it, right? We call this ion polarization. And we can recognize that greater ion polarization essentially means a greater attraction between ions, right? And when it comes to lattice energy, greater polarization is a sign of a more exothermic delta H lat, right? But this ion polarization also plays into another trend, and that is thermal stability. So, what is thermal stability? First, understand thermal decomposition. So, let's say we're looking at our group 2 carbonates, right? Let's look at calcium carbonate. This will decompose with heat, hence the thermal, to its metal oxide and carbon dioxide, right? That is thermal decomposition, right? And these will have, remember, this is breaking bonds, so this will have a positive delta H, right? So we can kind of understand the trends of stability by looking at ion polarization. So let's look at calcium carbonate versus, let's do barium carbonate for a big difference. So here's the thing. Calcium carbonate decomposes at 900 degrees Celsius, while barium decomposes at 1,360 degrees Celsius. So as we can see, barium is more stable. The carbonate of barium is more stable than that of calcium because it decomposes at a higher temperature. It requires more energy to break it, right? So let's look at these are the temperatures, and then over here, the delta H of decomposition. For calcium, it's For calcium, it's plus 176. For barium, it's plus 268. So the decomposition of barium carbonate is more endothermic than that of calcium. Why is that? Because it's more stable, right? And more stable means, one, higher temperature to break, but more energy to break, right? So why is that? Well, look at this, right? If you look at your periodic table, calcium in group 2 sits it sits 2 spots above barium, right? With strontium between it. So as we know, as you go down a group in the periodic table, you have a larger ionic radius, right? So what that means, keep in mind, calcium and barium both have 2+ charges with their carbonates, right? But calcium has a smaller ionic radius than barium. Oh, that's a 1+, whoops. So what does that mean? Well, if we remember from the ion polarization that we just talked about earlier, let's look at our charge density equations, right? We know that these both have a 2+ charge, right? 2+ and then 2+. Let this be volume 1, let's be volume 2, right? Volume 1 over volume 2. So the charge density, since volume 1 is less than volume 2, that means this charge density turns out to be greater. So the charge density of calcium is greater than that of barium. So when it comes to ion polarization, calcium will distort the carbonate anion more than barium does. Right? And here's the thing. Greater distortion means, let me see how the book phrases it. The way I'm thinking of it is greater distortion means it's almost like think of like a dipole, right? Think of like HCl. This has a dipole within it because the electrons sit closer to chlorine. It's essentially the same thing, where relatively electrons sit closer to calcium than they do to barium because of ion polarization. And the greater the greater this imbalance of the sharing of electrons, the weaker the bond because the easier to break, right? So because of that, that is why barium has a more endothermic delta H of thermal decomposition. It's why it decomposes at a higher temperature, because it polarizes its anion less, which means it has a stronger bond due to it sharing electrons more equally. So that's the idea behind ion polarization. It's a trend that seems to pop up a lot in tests, and it's good to know. All right. But yeah, that distortion, that imbalance of electron sharing makes it easier to break apart the bonds within your anion. All right, next thing. Titration. And then that's it. Okay. All right. So, next thing. Enthalpy change of solution. So, as I mentioned earlier, this is going to be our delta H solution. It's abbreviated by delta H sol, right? Here's how this works. What is delta H solution? It is the change in energy of a solid compound to its aqueous compound, right? And this can be positive or negative. So let's look at NaCl as a solid. You could write just an arrow going straight to NaCl aqueous, or you could denote it as NaCl plus AQ to show like the addition of water to form its aqueous compound, right? So the true definition of this is delta H solution is the change in energy when, let me see what my notes say. Born-Haber, got that. It is so delta H solution is the energy change when 1 mole of an ionic solid dissolves in water. You can just say that. So, I mean, literally, it's like, imagine literally like taking table salt from your kitchen and putting it in water and letting that dissolve. That is enthalpy change of solution. It's that simple, right? So enthalpy change of solution pairs with, one second. Okay, so we can first understand what these numbers mean, right? So, for instance, and by numbers, I mean what I'm about to write. So the enthalpy change of solution of magnesium chloride is negative 55 kilojoules per mole, right? Enthalpy change of solution for sodium chloride is positive 3.9 kilojoules per mole, right? So as we can see, magnesium chloride has a much more exothermic enthalpy change of solution. What does that mean? As I mentioned earlier, more negative means more exothermic, means more feasible. It's more spontaneous. So magnesium chloride dissolves more easily in water than sodium chloride, right? Because it has a more exothermic delta H of solution. So we can kind of understand the reasoning for this by looking at hydrogen, what do they call it? Ion dipole bonds. Sorry. Ion dipole bonds. So the idea behind this is that, so like our magnesium chloride or our sodium chloride structure, right? You have a lattice of positive and negative ions alternating between your sodium and your chlorine, right? And the idea is that in water, so obviously water, H2O, looks like this, right? Between oxygen and hydrogen, we have a dipole. And the idea of an ion dipole bond is that this negative dipole of oxygen actually bonds to a positive ion of our lattice. So what we can do, we can draw like a little bond, like that, and vice versa. Actually, I'll draw it on the other side. The positive dipole on the H attracts to the negative ions. So these are our ion dipole bonds that we see when it comes to dissolving something in water. So enthalpy change of solution is essentially it's essentially the difference in energy between the energy it took to dissolve this and the energy formed from these bonds. But that's kind of a bit beyond what you need to know. Just kind of understand where these ion dipole bonds come from, because they might mention them on the test. And this kind of makes sense to why Because, I mean, as you saw, I cannot think straight. The enthalpy change of solution of magnesium chloride was more negative. The reasoning behind this, at least from what I understand, is because, so obviously both of these lattices have chlorine as their anion. But magnesium chloride, the anion is Mg2+. And as we saw earlier, this 2+ from magnesium is going to have a greater charge density than sodium, right? And that greater charge density will create a greater attraction to that negative dipole. And as we saw with delta H lattice, that greater attraction means more exothermic delta H value. So that's my understanding of where that more exothermic value comes from. All right. So branching off of that, we have enthalpy of hydration. Which is delta H, HYD. So here's the difference. This is very similar to delta H solution. So delta H solution was going from a solid to aqueous. Hydration is going from a gas to aqueous. So the example it gives is calcium. And once again, you could denote this by writing the plus AQ, or you could just write it straight out. These reactions are always exothermic. Because think about this, right? Gases have more energy than liquids. I mean, think about, in gases, particles move more freely, more rapidly. So we're going from lots of energy to less energy. So we have a negative change. Exothermic, right? Cool. Okay, so the trends of this enthalpy are the exact same of delta H lat, right? So the greater your charge density, the more negative your delta H hydration, right? And for similar reasons to what we saw before, it allows these ion dipole bonds to be more easily formed with a greater charge density. So let's say you're comparing lithium and sodium. These both have a +1 charge, but lithium has a smaller ionic radius, so it has a greater charge density. Its charge density is greater than that of sodium's. I don't know why I'm writing this, but so that means lithium will have a more exothermic delta H hydration. Likewise, let's compare magnesium and lithium. So this thing here, right? Actually, no, sorry, not lithium. Let's do sodium. I don't know why I picked lithium. So these have, not only does magnesium, because magnesium sits to the right of sodium, right? So that gives it a smaller ionic radii as it is, right? Because, we decreasing radii to the right across a period. And it has a 2+. So not only does it have a more positive charge, it's also a smaller volume. So that's even more charge density for magnesium, meaning it has a more exothermic delta H hydration. And once again, reason for that is because greater charge density means more feasible to make those ion dipole bonds, which obviously it's to turn aqueous, you have to make ion dipole bonds. I mean, bonding with water via ion dipole bonds is what makes you aqueous. So the easier it is to form those bonds, the more exothermic your hydration or your solution enthalpy values. All right, so now let's relate all of these, right? So I kind of gave a sneak peek to it earlier, but let's look at this, right? top, we have delta H lat, right? So as we know, delta H lat is from our gaseous ions to our ionic compound, which is a solid, right? Down here, we have our aqueous ions. We know that going from gaseous to aqueous is delta H hydration. And going from our solid compound to aqueous is delta H solution. So from this, we can draw indirect routes. So delta H lat is equal to the indirect route, which is in flow with hydration, so that stays positive. Plus, we're going against solution, so that means that turns negative. So what that means, delta H hydration is equal to delta H lat plus delta H solution. It helps to memorize this equation, but if you ever forget it, you can always look back to this Hess's cycle and derive it from here. So this equation is helpful in determining trends in solubility of different compounds. So let's see what example they give. And keep in mind, they could also throw you a Born-Haber cycle diagram with these instead. So to kind of give a quick, I guess, sneak peek of what that would look like, right here would be your gaseous ions, give sodium fluoride. So I guess I'll kind of walk through the process, right? So let's say it gave you this diagram. And it said it wanted you to find delta H of solution for this diagram, right? Well, first I know, okay, well, if I want to find delta H solution, I need to find someplace on this diagram to fit that reaction. So what is the reaction for delta H solution? It's going from a solid to aqueous, right? So going from solid to aqueous would be going from solid sodium fluoride to from solid to aqueous sodium fluoride, right? So I know that delta H solution of sodium fluoride is exothermic, so I know I'm going down, and that gives us aqueous sodium fluoride, right? So now it's like, okay, I'm getting somewhere. Look at this, right? If I want to go, because remember, like when you're constructing a Born-Haber cycle diagram, you want to make sure that your platforms all connect in a cycle, right? So I need to find a way to connect this platform with this platform. That was stupid. To connect this with this and to connect this with this, right? Because remember, Born-Haber cycle diagrams have two pathways essentially. They kind of make like a full circle. So how do I go either from aqueous to gaseous or gaseous to aqueous? Well, I know delta H hydration, which is gaseous to aqueous, right? So I know that that's going to be going down this way. So to understand this, right, you wouldn't write this as just delta H hydration. You would need to express that this is really two steps. One of them is delta H hydration of sodium, and the second one is delta H hydration of fluorine, right? Whoops. So that's how you would express that step from this top platform down to this bottom platform. Same thing, it's got the same exact principles from the previous cycle. Like let's say we were dealing with magnesium chloride, right? Let's say I had 2 moles of this. as a gas, right? If I wanted to go from 2 moles of Cl minus to 2 moles of Cl aqueous, right? That would simply be 2 times its hydration value. So just keep that in mind. The same principles apply. So that's that step. I've expressed that step using delta H hydration. Now, how do I get this step? Well, think. How do I go from solid to gaseous or gaseous to solid? Well, guess what? I know that gaseous to solid is just delta H, a lattice energy, right? So boom, I've completed my cycle, and from here I can calculate what I need, right? So let's say I wanted to find delta H solution, right? So that I know that delta H solution, well, actually, what I'm going to do, right? I know that delta H lat, right, was going from this platform to this platform. So that is one side of the diagram. The other side, it's like, okay, I can get to this platform by going this way, or I can get it by going this way, right? So one side of the equation is one path, and the other side of the equation is the other path, right? So the other path is going to be our hydration steps, Na plus the hydration of, I'm keeping this positive because I'm starting from this platform up here, and as I'm going down, I am following this arrow. So we keep it positive. We do not multiply by -1. Right? Then my next step of this path is to go up like this, right? And look at this. By going up, I am going against the arrow for delta H solution. So it's going to be plus negative delta H solution. From here, isolate whatever variable you're trying to solve for. They'll give you values to plug in, and then boom, find your answer. A little side note. When I was constructing this diagram, I said I know that delta H solution is negative, which allowed me to understand that this arrow points down in the beginning, right? Let's say that you didn't know which way, because delta H solution can be positive or negative, right? So let's say you didn't know which direction to point that arrow. Well, look at this, right? If I had mistakenly drawn this arrow going up, that would have placed this platform here, right? So when I'd be following this other path, guess what? I'm still going against the enthalpy change of solution. So I would end up with the exact same equation, right? Which means I would end up with the exact same answer. So while the diagram may look wrong, it will still get you to the right answer. Now, they could be picky and want, like, if the question asks you, like, because like some questions will be like, calculate the value, it may be useful to construct a diagram. Other questions might be like, construct a diagram. So if they're picky about it and you realize that you messed up in the direction of an arrow, go back and change it, right? But understand that getting an arrow to point the wrong way, while it visually might, mean something else, it's not going to mess up your calculations. So don't worry about that. All right. The next thing is solubility. So, okay. Here is a very weird trend that they like to mention. Trends in solubility, right? Basically, remember this equation from before? Lattice energy equals hydration minus solution, or let me just write that back out over here. Lattice equal to hydration minus solution. I'm going to solve for a solution to get this. Right? That was derived from these equations right here. Here's the thing, right? We know, so here's a weird thing, right? Hydration and lattice energy follow the same trends. and that they get more negative the closer you are to fluorine, right? But here's the quirky part. So the example it gives here is with some different sulfates. So we have magnesium sulfate. Let's compare magnesium sulfate and barium sulfate, right? And then we have solubility, which is in moles per dm cubed, 1.83 and 9.43. Whoops. Times 10 to the negative 6. So as we can see from these numbers, the solubility of magnesium sulfate is higher than that of barium, right? Solubility essentially means when you dissolve this in water, how many moles how many moles of this will dissolve in 1 dm cubed of water, right? That's what it means, or 1 liter of water. So obviously the higher number means it's more soluble, right? So we can look at this equation to understand these trends, right? So here's the thing. Magnesium sits above barium in its group, right? Calcium and strontium are between it, right? As we know, this means that barium has a larger ionic radius, right? And as we understand from delta H hydration and delta H lat, this larger ionic radius, or just being lower in the group on the first place, means that barium has a less exothermic or a more endothermic hydration and lattice, right? But when you're trying to deduce, because obviously these solubility numbers, the greater the solubility, the more negative the delta H enthalpy, the enthalpy change of solution, right? So that means magnesium would have a more negative delta H solution than barium, right? Because it's more soluble. And remember, more negative means more feasible. In this case, more soluble, right? So as we can tell, down the group, delta H hydration and delta H lat, they both become more endothermic. But here's a weird thing. The rate at which they become more positive is not the same. It is said that delta H hydration, let me double check this. Yeah. It's said that delta H hydration becomes more endothermic, more positive at a faster rate than delta H lattice. The reason for this is a bit beyond what you need to know, but it kind of helps to understand. Basically, for hydration, right, as we know that ions with, basically, the greater the charge density, the more exothermic your delta H hydration, right? So the idea behind this is that as we're going down the group, because we're going from magnesium sulfate, right, to barium sulfate, we have to understand that delta H hydration is only dependent on essentially, this is a really weird one to explain, but basically the idea behind it is that the change in ionic radius is more significant to delta H hydration than it is to delta H lat. So the idea behind it is that the size of the anion is more significant when it comes to delta H lattice. But since delta H hydration doesn't really have anything to do with the size of the anion, it has to do with the charge density of the cation, right? So, sorry, I'm completely lost my thoughts, and I thought for a second that in a previous part of this video I got cation and anion mixed up, but cation is positive, anion is negative. Basically, okay, right. Delta H lat is this is so, just bear with me, guys. Delta H lat it is influenced by both the cation and anion, right? Delta H hydration is only primarily influenced by the cation. So as we're going down the group, right, the only thing that's changing is our cation. We're going from Mg2 plus to barium 2 plus, right? So when all of the significance is in the cation, and the only thing that's changing is the cation, hydration will change at a faster rate. The idea is that a greater portion of the significance for the influence of delta H lat comes from the anion. And since the anion's not changing, delta H lat isn't changing that much. So if we look back at our equation, right, delta H hydration minus delta H solution, since this is going to become more positive than this, because remember, this changes at a faster rate, that means as we go down the group, it's like subtracting 5 minus 3 to then subtracting like 100 minus 10. So our delta H solution is going to become more positive. And what do we understand about the numbers of delta H solution? The more positive means more endothermic, which means less feasible of a reaction, which means, in this case, less soluble, which is what we saw up here with these numbers. So that explanation was like super choppy. But this whole idea of understanding of like what is a bigger influence, all you really need to know is that hydration increases at a faster rate than lattice energy, which, long story short, more times than not means that delta H solution becomes more endothermic down the group, which means we become less soluble down the group. There are some exceptions to this trend in terms of the type of anion used, but fully understanding and predicting those trends with different anions is a bit beyond the scope of this content. You just really need to know this general trend. And here's the thing, right? Let's say they threw an example at you where delta H solution was becoming more soluble down the group, which means more exothermic down the group. Well, we know delta H solution is delta H hydration minus delta H lattice, right? So if it's becoming more negative, that means the opposite is happening. Instead of hydration increasing at a faster rate, lattice is increasing at a faster rate, right? So that would be going from, something like 3 minus 5 to 10 minus 100, right? So from -2 to -90, which is the opposite of what we saw before. So understand that if it actually is becoming more soluble down the group, which it most likely isn't, most examples have it become less soluble, not more soluble down the group. But in the instance where it is more soluble, aka more exothermic down the group, understand that means that lattice energy in that case is increasing at a faster rate. What does that mean? Back to the explanations that we saw before. That means that the lattice energy for that particular compound has a smaller amount of significance toward the anion. It's going to put more significance toward the cation. Again, really intricate stuff. You don't really need to know this much of it. It's just kind of like a bonus, helps to know it kind of thing. But for them to ask you this much depth on the test, like I kid you not, on some tests that I've seen, all you need to get that mark is like, it might ask, like a question could be, explain why solubility of group 2 sulfates decreases down the group. Explain why that happens. And all you would need to say, literally 1 mark would be stating that equation, right? You know the equation. That's 1 mark. Another mark would be saying that so let's say it would be saying ionic radius increases down group So delta H hydration and delta H lat become more positive. That's another mark. And then the last mark would be saying, in this case, since solubility is decreasing, well, I know solubility decreasing means that delta H hydration is increasing at a faster rate. If it asked why does the solubility of a certain type of compound increase down the group, instead of this last bullet, you would say that delta H lat increases faster than delta H hydration. That's all I got for this video. Make sure to like, comment, subscribe. I'm going to college, so I need money. Feel free to donate. Hit me up, But I'll be working on more chapters in the future. I'll try to keep in contact, let you guys know when those will be coming out.